Okay, hi. Today we're going to present our approach to the Inchworming rover and locomotion policies for the rover on inclined slopes. So how we're going to tackle this problem, how we're going to tackle projects, I'm going to first talk about, first talk about how Inchworming rovers are important, and then we'll see the different model choices we made and how MPC was implemented and its added value. And then we'll see our experiments and results that we had with our coding. So Inchworming rover is quite important because whenever you're tackling hostile or extraterrestrial environments, you're going to encounter some difficulties. You could be entrapped in sand, and in that case, there's absolutely no use to driving your wheels. You just get entrapped more. So that's where the Inchworming rover can have net value, because you can, with the angle, this angle you can choose with your arms, you can make two different phases, which is the expansion phase and the contraction phase. And when you expand, you will have your one wheel blocked and the other will go forward, and the other way around contraction phase, which makes the rover capable of going out of certain situations. So let's look at how we modeled the Inchworming rover.
To develop a controller, we first needed a model of the system. For the sake of time, we reduced the system into a two-dimensional kinematic model that relates wheel speeds to arm speed in a no-slip setting. In this model, a single input controls the acceleration of both arms, which in turn determines the behaviors of the arms and wheels. Since we don't account for slip, inchworming is probably not an optimal locomotion pattern, so we manually enforce inchworming through binary variables that force the model to move one wheel at a time. We then designed our MPC controller. Rather than using a terminal constraint to move the robot, we opted to penalize distance from the goal and the cost for more flexibility. We also have an energy term in the cost and explore robot locomotion patterns with and without energy penalization. The controller uses our simplified model and has lower and upper bounds on states and inputs. Additionally, the binary variables controlling the model are included as decision variables so that the controller has control over expansion and contraction. Extra constraints are included to ensure inchworming motion and prevent impossible robot poses. The following parameters were used for the model and controller. These parameters are roughly comparable to a real inchworming rover developed by the Embodied Dexterity Group at Berkeley. We use a CFTOC horizon of 5 and an MPC horizon of 30 for all experiments.
We first started our experiment without energy cost to test the feasibility of our MPC model. By minimizing the distance cost, the MPC can bring our model to the target location. Because of the simplified rover dynamics, we expected to see a simple and patterned locomotion policy. However, as you can see in the joint trajectory and the simulation video, the Inchworming rover shows a sophisticated locomotion generated by our model. By analyzing the trajectories, we could confirm that all model dynamics and constraints are satisfied. To reduce the computational cost, we ran the simulation for 30 time steps, and we could see the rover reaches to 2.25 meters for the time period. Now we included an energy cost in our model. The energy cost was derived from the rotational kinetic energy and potential energy of the rover components. For rotational kinetic energy, only swing motion of the arms is considered because wheel rotations are coupled to the arm swings, and to reduce the computational cost of the model. The potential energy describes lifting and lowering of the rover body because of the body height depends on the arm swing angle. In addition, slope angle parameter is incorporated into the height to reflect different energy on different slopes. With the energy cost, we expected the model to travel less distance compared to no energy case, and that was validated by the result. With energy cost, the rover traveled about 0.25 meter less than no energy case. In summary, we were able to develop a simple MPC model for Inchworming rover with simplified system dynamics and constraints through the project, and our model achieved a successful control policy optimization. The model validation and evaluation were conducted through the rover center of the mass and joint trajectory analysis. For future works, we want to expand the MPC model development to incorporate a more complex system to reflect realistic costs and constraints. At the end of the day, we will implement the final model onto the physical rover hardware for validation and performance evaluation against the existing open loop control policy.